Hi, welcome to Data Structure and Algorithm course. In today's session, we'll be discussing about what exactly is BigONotation. We have seen in the previous session that analyzing the running time of an algorithm by using a clock and watching that how long the program took to execute is not a good idea, because there are various factors like other programs, the hardware, the CPU, the data input output, and various other factors which might impact the running time of a program. So if you use a clock or watch to find out whether the program was slow or fast, or whether it is an efficient program or not, it is not a good idea. So what we should do is that we should find or develop a mechanism which will not depend on running the program to compare the two programs. You can use that factor of running the program in a computer in some special cases, but in majority of the cases that is not a good idea. So now we'll go and discuss about a technique called BigONotation, which is used to find out whether a particular algorithm is slow or fast, or whether an algorithm, two algorithms doing the same thing, when compared, which one is good or which one is not good. So that kind of analysis we'll do using a technique called BigONotation. Okay? So let us understand. So what exactly BigONotation mean? In a computer science, BigONotation is used to classify algorithms by how they respond in their processing time or working space requirement to changes in input size. So see the few things. Let us understand few things here. First, it says it is used to classify. It means by using a BigONotation, you can say this algorithm is better than that algorithm, this is a slow algorithm, that is a fast algorithm. So BigONotation help you to classify. Point number one. Point number two, it also helps you how they respond to changes in input size. So depending on how the input is, let us assume input is one input, two input, the data size is 1, 2, small, medium, large. Depending on how the input size increases, how long it takes. Is it linearly that execution time is there, or is it exponential? Is it square? Is it of second order of execution? So depending on the input size, how the algorithm time behaves, or the response time, processing time, or the working space requirement, or the memory requirement changes with the input size. So BigONotation is used for two purposes. One is to classify, and other is to find out how they respond with the changes in input size for the processing time and working space requirement. Okay? In other words, BigONotation is used in computer science to describe the performance or complexity of an algorithm. We also call it is an analysis of complexity of an algorithm. And how do we find out this and all of that? We'll discuss it very soon. But very simply, it is used to describe the performance or complexity of an algorithm. Big O specifically describes the worst case scenario and can be used to describe the execution time required or the space used, for example in memory or on disk by an algorithm. So we generally find out what is the worst case scenario that this algorithm will do. Now, when you approach the BigONotation based analysis of an algorithm, instead of trying to determine the specific execution time of an algorithm, what we do is that, very important, we simply count the number of primitive operation. Okay? We count the number of primitive operations that are executed. So instead of counting the time, we count the number of primitive operations. Now, what is exactly primitive operation? And how do you count it? And how does it help to find out the order of algorithm? Don't worry, just hang on. We are going to discuss each one of these one by one. So first we'll explain that in BigONotation, the fundamental concept is we count the number of primitive operations that are executed for a particular algorithm. So what we'll do is that in step 1, we'll calculate the number of primitive operations. In step 2, we'll find the functional dependency of these operations as per data input. So now number of primitive operations which is done, how that relates to the size of the input. And then in the step 3, we take the highest power term in the function which we define. In this function. Functional dependency, when we will find, we'll check the function. We'll understand all these steps in the following slides. So don't worry about that. We'll just do it soon. So what we'll do is that, let us first understand what is primitive operation. So what exactly is primitive operation? What is primitive operation? Once we understand that, then our question is, one of the problem is solved. Primitive operation means any programming step in your source code of Java, C, .NET, whatever language you are writing, does not matter, which includes any of these types of steps. These types of steps is called primitive operation. Is called primitive operation. So what are those steps? Primitive data operation, like I equals to I plus 1. This has two primitive operations. Assigning value to a variable. Primitive data operation means addition, subtraction, multiplication. All of those primitive data operations will come here. Assigning a value to a variable is also called a primitive data operation. Calling a method is called a primitive data operation, primitive operation. Performing an arithmetic operation like addition, subtraction, multiplication, division, all of them. Comparing two values equal to, less than, greater than, and all of that. Each one of them is counted as one primitive operation. Indexing into an array, whenever you put a data object into an array, that is also called a primitive operation. Following an object reference, when you are assigning a reference to another object, that is called one primitive operation. Doing a returning from a method is also called a primitive operation. So these are the various operations. These are called primitive operation. Okay. So these are various primitive operations which are there, which we will count in any source code in any language. And once we know what is primitive operation, how to count them, we'll use this concept in a next step for finding out your BigONotation. So stay there still. First understand what is primitive operation. Okay. Once you understand, it is much easier. So everybody is clear what is primitive operation? A primitive operation is nothing but a type of step which is used for BigONotation, and those steps are these: primitive data operations, assigning a value to a variable, calling a method, performing an arithmetic operation, comparing two values, indexing an object into an array, following an object reference, and returning from a method. Now let us take one example. Okay, we had an example that find number of primitive operation in a given algorithm. How do you find? Let us take one example. We understood what is primitive operation, but now what we'll do is that we'll try to calculate number of primitive operation in an algorithm. So here is one algorithm. This is one algorithm. And we'll try to find out how many primitive operations are inside this algorithm. So that is what you could do. Now let us find out all the primitive operation into that algorithm. So this is the algorithm, and we'll find primitive operations. So let us start counting. How do you count the primitive operation? Let us see. I will show you how I am counting. First one, let us see that this is start with array max s. So the operation starts after this curly bracket. Here is x equals to s0. There are two operations. First is you are assigning x equals to something. So this is called assignment, and you are trying to find out the object which is at position 0. So that is called indexing, and that is another operation. So that's why there are two operations called for indexing and assignment. So there are two primitive operations here. Okay. Now come to the next line, for loop. For I equals to 1, I less than s dot length, I plus plus. Now how many primitive operations are here? Beginning of loop, one assignment, and that is here, I equals to 1. Okay. So I equals to 1 is this one. Okay. On entering each iteration, n, one comparison, and that is this one. N times it will enter, so it will be one comparison n times. Now each iteration, that n minus 1 iteration, because it will do each iteration, it will come if si greater than equals to x. So there are two operations here, indexing and comparison. So this is two operation, indexing and comparison, and then x equals to si. This is 0 or 2 operations, indexing and assignment. Now why it says 0 or 2 operation here? Because if this condition is not valid, then this step will not get executed. So sometime there will be 0 operation here, sometime there will be 2 primitive operation here. So let me just repeat again. X equals to s0, there are two primitive operations, one is indexing and other is assignment. In the for loop, we start with I equals to 1, so there is one assignment operation, primitive operation. Then we go I less than s dot length, so there are one primitive operation, that is comparison I to this. Remember, s dot length is not a method, it is a variable. So there is only one primitive operation here, and then we come inside this, and each iteration, will be n minus 1 iteration. And that is if si is greater than x, because we say I less than s dot length, so we are not saying s equals to s dot length. If it was equals to, then there was n iteration, but if it is I less than s dot length, then there is a n minus 1 iteration. And once we enter inside, this statement will give you two primitive operations, one si for indexing and one greater than comparison for comparison. So there are two primitive operations at this point, and then x equals to si will give you either 0 or 2 operation, one for indexing and other for assignment. Okay. Now after this one is done, what happens? This do loop x equals to si goes back, and there are another one which comes here, I plus plus. Now this I plus plus become end of each iteration, that is n minus 1 times, and there are two operations, summing and assignment. So this is your I plus plus 2 primitive operation. This is I plus plus is nothing but I equals to I plus 1. So I plus 1, 1 primitive operation, I equals to is 1 primitive operation. So that is 2 primitive operation. And in the end there is one final return which is just 1 primitive operation. This is this one. So this is the way you calculate a primitive operation in a given source code. Once you calculate the primitive operation, next step will be how do we use that information. Okay, so let us assume that we calculate this primitive operation. Now the number of primitive operations Tn executed by algorithm array max is n is the, here n is the size of the input array. Now what I have done is that we have added everything. Now 2 plus 1 plus n plus 2 plus 2 star n minus 1 plus 1. So it is coming from here. 2, so here is, you see that. Okay, so this one is 2, this one is 1, this one is n into 1, so that is n, and this one is n minus 1 times 2 and 0 or 2. So we will say worst case and best case, right? So worst case is 2 plus 2, best case is 2 plus 0. So it is n minus 1 into 2 plus 0, that is best case, and then this one is n minus 1 into 2. This is our best case. Okay, so this is best case scenario. We'll add 2 plus 1 plus n minus 1 star 2, and then n minus 1 star 2, and then there is 1. So 2 plus 1 plus n minus 1 star 2, n minus 1 star 2 plus 1. So if we add all of this, we'll get the best use case scenario. If we want the worst use case scenario, we'll have to add plus 2 here as well. So that is what we are going to do. 2 plus 1 plus n plus 2 plus 2 into n minus 1 plus 1. In the worst case scenario, that additional 2 will come here, 2 plus 2 star n minus 1 plus 1, and this will remain same. So the best case scenario says that the number of primitive operation Tn executed by algorithm array max, where n is the size of the input array, it will take 5n. So how many primitive operations are there? 5n and 7n minus 2. So 5n and 7n minus 2 are the number of primitive operations for an input of size n. Is it clear? Let me just repeat. Total number of primitive operation for a given input of size n is 5n in the best case. In the worst case, total number of primitive operations for a given size of input called n, in worst case it will be 7n minus 2 in this algorithm. Every algorithm will have a different number of primitive operations for a given n. In this particular algorithm, it is 5n and 7n minus 2. Okay, now you got it? Now once you have found this, there is another part of the analysis which is called average case of primitive operations. Now we have found the best case and the worst case. So this is best case and this is worst case. Sometime question comes, is there something called average case? It is possible theoretically, but it is very difficult to do and not very helpful. So what we generally do is that it is difficult to do and not even very helpful. So what we'll do is that we'll generally ignore a average case analysis. We only focus on best case and worst case analysis using a BigO notation. It is difficult, depends on the input distribution and requires a very heavy mathematics on probability theory, and it is not very helpful either. So we'll focus on best case and worst case only. Okay. Now best case and worst case, in algorithm only best case and worst case are considered. Best case means the shortest running time, worst case means the longest running time of an algorithm. So there is not much complexity there. Now once the function of primitive operation is done, in last one we had 5n, what was that? 5n and 7n minus 2, correct? So let us see that we had 5n, function was 5n, number of primitive operation was 5n, and in other case it was 7n minus 2. That was the worst case and best case. This is best case, this is worst case. Once the function of primitive operation is done, we consider the largest term in this function, big O notation, a practical method to finding BigO notation of a function. So what we do is that we use the notion of a largest term in a function. What is the largest term in a function in this? N. The term with the largest exponent of n, the term that grows the fastest. So it is very simple. Think about this one. Okay, let me just show you one example. So now if you write a function n equals to n cube plus n square minus n. Now what is the largest exponent of n? It is 3, right? And which term grows the fastest? It is n, this term, n cube. When you increase n, the rate at which each of these terms will grow, this one will be growing at the fastest rate. And this is called the largest term in a function. Now, if I have another function, n square plus 100n, which one is growing fastest? Again, if you see, this one is growing fastest. This is the largest exponent of n and growing the fastest. So we have to find the largest term in a function. Now what is fn? Fn is nothing but this one. We have calculated fn. Fn is nothing but the number of primitive operations when input is n. Total number of primitive operations when input is n, that is called fn. Now inside fn, find out the largest term in a function, and that largest exponent of n, that term itself becomes the order of the algorithm. So we call it, if for a algorithm fn is like this, then this is called a algorithm of order n cube. Okay, this one will be called an algorithm of order n square. Now in these cases, largest term is n. What is the largest term? N. So this is called a algorithm of order n. Okay. So depending on what is the largest term, if it is function n, as a total number of primitive operation comes like n cube plus n square minus n, then it will become like that. So that is the way you calculate a order of an algorithm. Now, why we call it highest term in a function? In this example, let us assume phi pen is the term which grows at highest factor compared to other terms. How? See this. Let us assume that we have a function called phi pen plus log n plus 7. In this one, you increase n and you see that how the two terms are increasing. While you are increasing n, which one is growing faster? This one or this one? Phi pen will increase like, write it here, okay? So here is log n, here is phi pen, okay? Now for n equals to 1, it will be 5. For n equals to 2, it will be 10. For n equals to 10, it will be 50, sorry, 50. For n equals to 100, it will be 500. For n equals to 1000, it will be 5000. Now, tell me one thing. Out of this and this, which one is growing faster? This one is growing faster or this one is growing faster? It is very simple that this one is growing faster. And the term which grows at highest factor compared to other terms is taken as an algorithm. So this one again will call an order of algorithm n. Now if a function does not have n, what happens if the function is like this? Suppose you have a function n equals to 10. There is no n. If your function n is like 100, what is the order of algorithm in these two cases? Whenever you have a constant and there is no n, in such cases, the algorithm of these become order of 1. So this becomes order of 1. This is called a constant algorithm. So irrespective of the input size, it always gives the same number of primitive operations. So the number of primitive operations, when it is constant and independent of input size, it is called of order 1. And that is what is the example of this one. If primitive fn is 100, then it is of order 1. If it is f 5 by 9, then order is 1 by n. So this is called order of algorithm calculated based on number of primitive operations done in an algorithm. Okay? Now there are various types of big O notation of function and all. If it is a log n, then it is called, now there are various names given to these algorithms. Some are called logarithmic if it is of order log n. It is called linear if it is of order n. It is called quadratic if it is of order n square. It is called polynomial if it is of order nk, where k is greater than or equals to 1. So these are also polynomial, but generally if it is n to the power 1 or 2, we call linear and quadratic directly. If it is n cubed, then it is cubic. Now exponential functions are different one, where it is of order a to the power n, where a is greater than 1. Can you find an algorithm which has exponential function? Think about it. Can you find out an algorithm which has exponential function? Think and find out and do the research. Also find out what kind of a algorithm you can create which has a quadratic function. This is just a thinking and brainstorming. Find out an algorithm which has a quadratic function or of an algorithm is of order n square. Now let us see one example of order of 1. What it means is that order of 1 indicates that given the algorithm will always execute in the same time or space regardless of the size of the input data set. What it means is that I am finding out if you give me an array of a string, then I will find out whether the first string is null or not. If you give me an array of a string and I have to find out whether the first string in an array is null or not. Now for that what I will do is that I will write this code: if string 0 equals to null, return true or return false. Now in this case, if you notice, it does not matter what is the size of the array string. This object may have 10 string or 10,000 string or just one string. In all the cases, it will still run these 3 steps and that's it. It does not depend on how big is the array of string. So this algorithm runs in a constant time or space regardless of the size of the input, and that's why it is called an algorithm of order 1.